Training in Weld Quality Assurance and Quality Control. Section 4, Discontinuities and Defects. Topic 4, the common causes of discontinuities related to internal inconsistencies and weld metal irregularities. The objective of this topic is to be able to identify the common causes of structural weld discontinuities as related to the welding procedure. As mentioned in Topic 3, it is essential to be familiar with the causes of weld and weldment defects so that they can be prevented by earlier or further inspection. To be able to do this, quality control personnel must have a working knowledge of the acceptance standards that spell out the acceptable limits for weld discontinuities. One of the primary jobs of a welding inspector is to ensure that welding fabrication is performed as specified in the weld procedure. Defects such as cracks, porosity, slag inclusions, tungsten inclusions, incomplete fusion, and inadequate penetration can be prevented during fabrication through careful consideration to the procedure variables. These all have a considerable effect on weld quality and must be analyzed to determine their cause as well as their acceptability. The first defect to be discussed is cracking, perhaps the most serious defect found in welds. There are a variety of different types, some of which have similar causes. Cracks are usually devastating to the strength of a weld or weldment, and therefore must be prevented in order to maintain high levels of quality. The two main types of cracks are hot and cold cracks, and can occur with most welding processes if procedures are not correctly followed. Hot cracks normally occur at elevated temperatures, above 400 degrees Fahrenheit, and typically occur in the throat, root, or crater of a weld. They are most often caused by specifying materials not recommended for welding, an improper selection of filler metal, poor weld shape, incorrect weld size, and incorrect methods of breaking the arc. Hot cracks can be caused by excessive amounts of sulfur, phosphorus, and lead in the base metal, which are commonly found in free machining steels that are designed for good machinability. Another element, selenium, is found in free machining stainless steels and can contribute to hot cracking. Metals containing these elements are generally considered non-weldable. Similarly, welding of contaminated or dirty edges can promote hot cracks. Some low-melting contaminants may tend to gather at the throat of the weld during solidification and produce throat cracks. Joint edges should be thoroughly cleaned before welding and between passes to prevent accumulation of contaminants. Another cause of hot cracking is the improper choice of filler metal for the base metal. This is especially important to avoid when welding non-ferrous metals such as aluminum. Hot cracks sometimes occur in the root passes of deep penetration welds. Such passes cause high contraction forces to be exerted on the weld deposit during solidification. If not repaired, these cracks can extend through additional weld metal in multi-pass operations. Welds that are too small for the plate thickness or excessive joint restraint caused by improper clamping or fixturing can promote hot cracks due to contraction forces during solidification. If this occurs, check the weld procedure for proper bead sequence or for recommended preheating procedures. These factors tend to reduce contraction forces. Hot cracks also occur because of improper methods of breaking the arc, which do not allow the crater to be filled to bead height. Hot cracks can be minimized or eliminated through the use of a runoff tab at the completion of the joint. This tab is later removed and eliminates any crater cracks that could propagate into the welded joint. Crater cracks can also be controlled, where possible, by decreasing the current and adding filler metal while the arc is being broken. filling the crater to bead height. This technique is most popular with the gas tungsten arc process and fills the crater while reducing heat input. The second type of cracking is called cold cracking and occurs after the weld metal solidification is complete. They may appear as toe, throat, or underbead cracks and can occur up to several days after welding is complete. In general, cold cracking is caused by rapid cooling of the weld and heat-affected zone in higher carbon and alloy steels. Excessive joint restraint and inclusions of hydrogen in the weld also contribute to cold cracks. These factors must be considered collectively when determining the cause of cold cracking. The higher the carbon and alloy content of a steel, the higher the hardenability. Hardenability is the ability of a material to become hardened. High carbon and high alloy steels produce high degrees of hardness in the weld and heat-affected zone when the weld is cooled rapidly. This causes the weldment to be more crack-sensitive and therefore prone to failure in many loading applications. Many engineers use a carbon equivalent equation to determine the hardenability of steel. Typically, this equation may be given as the sum of the carbon percentage plus reduced amounts of other existing alloys present in the material which affect the hardenability. In general, steels with a carbon equivalent over 0.40% are considered weldable, but require preheat to reduce hardness by slowing the rate of cooling. The amount of preheat increases with higher carbon equivalents and the thickness of the base metal. Thickness becomes important since greater thickness produces greater heat sinks, thereby increasing the cooling rates that contribute to cold cracking. Another common cause of cold cracks is high joint restraint, which promotes high residual stress in the weld and the heat-affected zone. This residual stress is caused by the non-uniform thermal expansion and contraction forces brought about by the heat of welding. Excessive joint restraint can be caused by rigid clamping, thick sections, and the geometry of the joint and the weldment. These factors cause contraction forces to be accepted by the weld and heat-affected zone during solidification in the form of tensile stresses. Again, preheating is often used to reduce the non-uniform heating and cooling of the weld during solidification, preventing high buildup of residual stress. Residual stress in the weld and the heat-affected zone can result in cold cracking when the part is placed in service, since additional loading can force the material above its yield stress and permanently deform or break it. Hydrogen entrapment in the weld and the heat-affected zone can also promote cold cracks. Hydrogen tends to form small cracks in these areas under the weld bead. Because of this, these cracks are often called underbead cracks. In service, such cracks tend to connect and cause weld failure. Hydrogen is produced from the breakdown of moisture in the weld joint, or from materials such as filler metals, fluxes, and shielding gases. In oxyacetylene welding, hydrogen can be produced by the chemical breakdown of oxygen and acetylene. Hydrogen can be reduced in the weld deposit through the use of low hydrogen welding processes, proper joint cleaning, and the use of preheat. Low hydrogen electrodes can be used, such as the E7018 electrode used with shielded metal arc welding. All low hydrogen materials must be stored properly to prevent moisture pickup. Holding ovens are often used for this purpose. Shielding gases may also add moisture to the weld joint. It is important to use only welding-grade gases which contain no significant moisture content. Preheating can be used to reduce the amount of hydrogen in the weld and heat-affected zone. This slows the cooling rate and allows more time for hydrogen to diffuse and escape from the weld deposit. All these conditions must be controlled if cracks are to be minimized or eliminated. If cracking still occurs, it may be necessary to investigate the details of the welding procedure to determine if the procedure is suitable for the design of the weldment. The next discontinuity to be discussed is porosity, which is caused by the exposure of molten weld metal to oxygen, nitrogen, and hydrogen in the atmosphere. It can be located within the weld or exposed to the surface. Porosity can also result from the presence of foreign matter, water, humidity, oil, grease, or other contaminants in the weld puddle. Porosity can be present as uniformly scattered, clustered, linear, or piping. The manner in which the porosity is distributed is helpful in analyzing the cause. For example, uniformly scattered porosity could be caused by moist or dirty base and filler metal, or improper welding technique. Cluster porosity is likely to result from improper arc starting or breaking, or periodic loss of shielding gas coverage. Linear porosity aligns along the boundary of a joint and is directly related to contamination in the base metal, weld metal, or both. Piping porosity results from breaking the arc too suddenly, which allows the puddle to cool too quickly. Conditions leading to porosity can be eliminated with the use of proper shielding of the molten weld metal, proper preparation of surfaces, and removal of moisture from filler and base materials. When shielding coverage is required, be sure that the gas is welding grade. Porosity is a common defect, as shown in this fillet weld, and can be minimized if the conditions of the welding procedure are carefully controlled. Slag inclusions are non-metallic solid materials trapped within a weld or between weld layers. They occur during solidification of the puddle and normally appear internally but may be exposed to the surface. The most common cause of slag inclusions is poor interpass cleaning, meaning that later welds of a multipass operation are deposited directly over the slag of the previous pass. Too low a welding heat or poor joint design will also cause slag to become trapped in the weld. Slag inclusions can be prevented by using proper welding technique, proper interpass cleaning, and meeting the joint design requirements of the weld procedure. A similar type of weld defect is the presence of tungsten inclusions, which are particles of metallic tungsten trapped in a weld. This defect can occur when gas tungsten arc and plasma arc welding processes are used. Tungsten can appear in a weld either scattered in fine particles or in one large piece when the electrode tip is broken off in the weld puddle. Noting how the tungsten appears in the weld can indicate the cause. If it is scattered in small, fine particles, it is possible that the amperage was set too high, or there was a lack of shielding gas coverage. These conditions cause the tungsten electrode to break down and scatter throughout the weld. Too high a hot start setting can also cause this condition. Large particles break off and lodge in the weld if the arc length or tip to puddle distance is not maintained and the tip comes in contact with the puddle. Scratch starting the arc can also contribute to large particle inclusions. For this reason, copper blocks are often attached to the work for scratch starts. The next defect to be discussed is incomplete fusion of the weld and base metal. Poor joint design and poor edge preparation are the two most common causes of this discontinuity. Another contributing factor is the presence of oil or dirt on the joint edges or poor welding technique. If the heat input is too low during welding, the molten puddle may not fuse well into the base material, and the weld metal actually flows out of the joint edges without fusing. Similarly, the heat from the arc is concentrated on the weld pool, preventing the melting of the joint edges. This is especially common with continuous wire processes. Incorrect work and travel angles can also cause lack of fusion, since this can prevent the concentration of arc force on the joint edges. Incomplete fusion cannot be detected without the use of a non-destructive testing method. Welding procedures are qualified through the use of destructive testing to ensure that the procedure variables do not produce this defect. The final defect to be discussed is inadequate joint penetration, or penetration which is less than specified. This defect is commonly located at the root of a weld and is generally caused by an insufficient heat input while welding. Too low an amperage is the usual cause. Holding too long an arc length or too long a stick out reduces the heat input and leads to inadequate penetration. Too fast a travel speed along the joint has a similar effect. Other contributing factors are an incorrect joint design or improper preparation of the joint edges. If a root opening is too tight or the groove angles are not wide enough, the weld metal may be restricted, causing lack of penetration at the root. To prevent incomplete penetration, it is necessary to ensure that enough heat is being used on a properly designed joint and that the welder or operator has the skill necessary to produce the desired weld. It is important to control the conditions that cause discontinuities related to internal inconsistencies, and if procedures are carefully written and implemented, most weld defects can be prevented. It is vital, therefore, for welders and inspectors to be familiar with the conditions that exist which may cause a weld or weldment to fail. Many weld failures can be minimized or eliminated if conditions are controlled before, during, and after welding with a well-written procedure and a qualified staff.